Many of the probability problems involving dependent events that were solved with trees in Chapter 8 can also be solved using counting principles, permutations, and combinations. And this can be very helpful when you have a large number of choices. So we're going to be working with bigger problems here that would make the trees just really not adequate for what we're going to be dealing with. Remember our basic probability principle. The probability of an event is equal to the number of outcomes in the event divided by the total number of outcomes in the sample space. In other words, probability of E is the number of events in E over the number of events in the sample space. We've seen this example before. In fact, we used a tree to solve it. From a potential jury pool with 1 Hispanic, 3 Caucasian, and 2 African American members, 2 jurors are selected one at a time without replacement. Find the probability that 1 Caucasian and 1 African American are selected. All right, so I'm going to talk you through this. First thing that we want to do is we want to figure out how many different ways 1 Caucasian and 1 African American can be selected. And we're going to use the combination for that. The Caucasian can be selected in 3 in combination with 1, so 3 choose 1 ways. And the African American can be selected in 2 choose 1. So we have the 3 choose 1 times 2 choose 1. It's 3 times 2, which is 6 ways. So that's going to be our numerator. Our denominator is how many ways 2 jurors can be selected, period, given the number in the jury pool, which would be 6 total. So it's going to be 6 choose 2 on the bottom, which is 15. So we have 6 on the top and 15 on the bottom, which leaves us with 0.4, which is what we got when we did this problem with the trees earlier. A lot less messy and a lot faster this time. Let's try this one. From a baseball team of 15 players, 4 are to be selected to present a list of grievances to the coaches. In how many ways can this be done? Pause the recording and give this a try, and resume to check your answer, and then go to the next part. Okay, this is just very simply 15 choose 4. So you're just going to use the combination. We've got the combination notation there. You've also got the factorial notation. You can put it straight into your calculator using the combination notation. And we have 1,365 ways to choose 4 players from 15. Now we're going to build on that problem. One of the players is Michael Branson. Find the probability that he will be among the 4 selected. Think about this, pause the recording, and resume to check your answer and to continue. All right, again, we need to find out the number of events in the outcome, the events that we want to happen, the outcomes we want to happen, over the total number of outcomes in the sample space. Now, if you think about this, we have to choose 4 people, but 1 has already really been chosen for us. He has to be included. Branson must be included among the 4 selected. So that really only leaves us with needing to find 3 more out of the remaining 14. So to find the number of ways that this can happen, we're just going to do 14 choose 3, which is 364. Now, the number of ways that 4 players can be selected from 15, I think we did that in the last problem, was 1,365. So we have 364 over 1,365, which is 0.267. Now find the probability that Branson will not be selected. Okay, we've talked about what happens when you see that word not before. See if you remember. Pause the recording, give it a try, and resume to check your answer. Well, we already figured out the probability that he would be selected, and that was 0.267. The probability that he would not be selected would be 1 minus that. It's the complement, which is 0.733. Okay, here's another example. A manufacturing company performs a quality control analysis on the ceramic tile it produces. It produces the tile in batches of 24 pieces. In the quality control analysis, the company tests 3 pieces of tile per batch. Suppose that a batch of 24 tiles has 4 defective pieces. What is the probability that exactly one of the 3 tested tiles is defective? All right, pause the recording, give this a try, resume to check your answer and to continue. All right, so they're symbolizing the probability of one being defective among the 3 as P1 defective. To find this, we need to know how many ways can we select 3 tiles for testing. Since the order doesn't matter, we're going to do 24 choose 3, and we find that we can select 3 tiles out of the batch 24, 2,024 ways. Now, there are 4 choose 1 way of choosing 1 defective tile from the 4 in the batch. Remember, there are 4 defective tiles. We want to know the probability of choosing 1, so that's 4 choose 1. If we choose 1 defective tile, then we must choose 2 good tiles among the 20 good tiles, and we can do that 20 choose 2. So we have to account for all 3. So it's going to be 4 choose 1 times 20 choose 2. And we get 760 for that. Now we put the 760 over the 2024 and we get 0.3755. B, if at least one of the tiles in the batch is defective, the company will not ship the batch. What's the probability the batch is not shipped? Now, we've already found the probability of selecting exactly 1. Notice this one says at least 1. Think about what at least 1 means. Remember that there are 4 defective in the batch, and remember we're choosing 3 at a time. Pause the recording, give this a try, and resume to check your answer. Okay, so the batch will not be shipped if 1, 2, or 3 of the tiles are defective. We've already found the probability of 1 being defective. We need to find the probability of 2 and the probability of 3. To find the probability of 2, we need to count the number of ways to choose 2 from the 4, and that's 120. So we're going to do that very similarly to how we did the 1. The 2 defective will be 4 choose 2, and then the third one would be find, that'd be 20 choose 1, and that would give us 120. To find 3 defective, we need to have 4 choose 3 times 20 choose 0, and that gives us 4. So we have the probability of 2 defective, we have the probability of 3 defective, we previously found the probability of 1 defective, and we get adding all of these together, 0.4368. Now use the complement rule to find the probability the batch will be rejected. Okay, you may have thought to yourself, there's got to be an easier way. Well, there is, and we're going to try that now. So pause this recording, give it a try, and resume to check your answer. It says we reject the batch if at least one of the sample tiles is defective. The opposite of at least one would be that none are defective. So what you can do is find the probability that you don't pick any defective. So it would be 4 choose 0 for the defective, 20 choose 3 for the good. That gives us 1,140. We already discovered that there's 2,024 ways to sample the tiles. So that gives us 0.5632. Remember, that's no defective tiles at all. We want the opposite, so 1 minus that gives us 0.4368. A little bit easier maybe than the last one, at least less calculation. Okay, let's move on to another example. In a common form of 5-card draw poker, a hand of 5 cards is dealt to each player from a deck of 52. There is a total of 52 choose 5 or 2,598,960 hands possible. Find the probability of being dealt each of the given hands. All right, so first of all, a heart flush hand, which means 5 hearts. So you need to consider that all 5 cards chosen were hearts. Pause the recording, give it a try, and resume to check your answer. Okay, there's 13 hearts in the deck, so 13 choose 5 is going to be 1,287. So there are 1,287 different hands containing only hearts. The probability, and we take that and we divide that by the 2,598,960 we found or they gave us actually as part of the example, as part of the explanation, and we get 0.000495. So in other words, you have a 0.05% chance of that happening. Now we're going to try a flush of any suit and a full house of aces and eights. So let's do B first. Pause the recording, give it a try, and resume to check your answer. Well, there's 4 suits to a deck, so instead of having to have hearts, we just take the probability that you get one particular suit and multiply that by 4, and we get 0.00198. And now try part C, a full house of aces and eights. So you have to have 3 aces and you have to have 2 eights. Okay, pause the recording, give this one a try, and resume to check your answer. All right, there are 4 aces in a deck, so you're going to have 4 choose 3. There are 4 eights in a deck, so that's 4 choose 2. You're going to multiply those together, and then the denominator is going to be the 52 choose 5, and that gives us a 0.00000923 probability of being dealt a full house of aces and eights. Now we're going to try to find the probability of getting any full house, 3 cards of one value and 2 of another. Pause the recording, give this a try, and resume to check your answer. Okay, a little bit more complicated. First thing you got to remember is that there are 13 values in the deck. That would be the values on the cards, A's, 2, 3, etc. There's 13 different ones. So you have 13 choices for the first value mentioned and 12 for the second. So in other words, if you got 3s the first time, that's a choice out of 13. For the second, because you have to have 2 different values, you've only got 12 choices left. Now, there are 13 different values, and each of those would be 4 choose 3. And then you have 12 different values remaining, and that would be 4 choose 2. So that's where we're getting the numerator from. And then the denominator is going to be what we've used since the beginning, and that's 0.00144 for the final answer. And another example, we have a cooler that contains 8 different kinds of sodas, among which 3 cans are Pepsi, Coke, and Sprite. What's the probability, when picking at random, of selecting the 3 cans in the particular order listed in the previous sentence? So you've got a cooler, 8 different kinds of soda, 3 cans are Pepsi, Coke, and Sprite. What is the probability you will pick them out of the cooler in that order? Pause the recording, give this a try, and resume to check your answer. So this time we're going to use a permutation because the order is going to be important for this. So we're going to find the number of arrangements in the sample, which is 8, permutation 3. So 8 times 7 times 6, or you can even put it in your calculator, and you get 336. Since each can is different, there's only one way to choose Pepsi, Coke, and Sprite in that order. So the probability is 1, because there's only one way to do it, out of 336, which is 0.0030. Okay, I think this is our last example. Suppose a group of 5 people is in a room. Find the probability that at least 2 of them have the same birthday. Okay, that at least gives you clues to how we're going to approach it. See if you remember. Pause the recording, give it a try, and resume to check your answer. All right, at least means 2 or more. So the easiest thing to do here, instead of finding the probability that 2, 3, 4, 5, and then adding them all together, the easiest thing to do is to find the probability that nobody has the same birthday and then subtract that from 1. And the probability that no one has the birthday is actually pretty easy. We're going to, first of all, when we talk about same birthday, we're not talking about years. We're talking about day and month. Secondly, we're going to ignore leap year because we don't want to overcomplicate things. And thirdly, we're going to assume that every day is equally likely for every person. So what we're going to do is we're going to figure out how 5 people could, what's the probability that 5 people could have all different birthdays. So how many different ways could that happen? Well, the first person can have a birthday any one of the 365 days. So 365 times 364. The second person has, any day but the one the first person had. 363, 362, 361. In other words, we're taking a permutation of 365 items taken 5 at a time. And the number of ways that 5 people can have the same or different birthdays is 365 to the 5th. So the total number of ways that 5 people can have birthdays during the year is 365 to the 5th. Okay, so that's going to be our bottom number. We have the permutation on top, we have the 365 to the 5th on the bottom, and we get 0.973. Now that's the probability that the 5 people will not have the same birthday. Nobody in that group will have the same birthday. The probability that at least 2 of them will is 1 minus that, or 0.027. The last example can be extended for more than 5 people. So we have a general rule. The probability that no 2 people among n people, n being any number, have the same birthday is 365p, in other words, permutation of 365 things taken n at a time over 365 to the nth power. And the probability that at least 2 of the people do have the same birthday is 1 minus that. This is a chart showing how many people can be in the group and the probability that at least 2 have the same birthday. It's kind of surprising because you would think that you would have to have a bunch of people in the room to get even close to having 2 people with the same birthday. A lot more than what you actually need. You'll notice that by the time you have a group of 23, you have at least a 50% chance that 2 of them will have a birthday on the same day. And by the time you get to 50 people, you have a 97% chance that at least 2 of those people will have a birthday on the same day. Be extra practice, so try the problem, pause the recording while you do it, resume to check your answer, and continue this way for the rest of the recording.